So looking at this, it seems super short, but there's a lot of information here. So in this first day, I don't know if I'm going to get through all this in one day. We'll see.
Tell by all the words how many.
So if we don't finish, talking about all this stuff, go ahead and work on the homework, but we'll continue talking about it next class period.
Well, the homework will be the next class.
So the homework will be due the next class period. But at least then you can spread out the homework. But I don't know how far we're going to get. We'll see. There's a lot of concepts. So the first concept I want to get across is that right here, pure substances. Because you're in lab, you're messing with the Abbey refractometer. And Jeff, you mixed what and what with the Abbey refractometer? Ethyl acetate and cyclohexane. So what you're doing is just trying to boil stuff and distill it, and you end up finding a eutectic mixture, and it's mixtures. This is pure substances. So all we're talking about is pick ethyl acetate, and we're talking about pure ethyl acetate. Pick water, we're talking about pure water. So physical transformations of pure substances. So that's the first point I want to get across. And then the book is going to spend a lot of time on these phase diagrams. And it starts out by saying, okay, a phase diagram is just pick a pressure and pick a temperature and what state is the most stable. And okay, that's easy enough, but it starts out by saying, okay, well, how do you determine which state is the most stable? It's the state with the lowest, what? What do we call mu? Chemical potential. And mu was really Gibbs energy, right? The molar Gibbs energy. So whatever state has the lowest chemical potential or molar Gibbs energy, that's the state that's going to exist at that pressure and temperature. Okay. And so then when we start talking about these phase boundaries, right? So here's a phase diagram, a general phase diagram. And I would know just the general phase diagram. This is a great one to know. It has all the parts. And different phase diagrams are going to look much more complicated. Look what's coming. They're going to get complicated and ugly, but the point is this one really has all the parts. So be familiar with it. And what you draw, the lines, you draw phase boundaries. So that's what's going on.
The regions between the transitions.
Yeah, between like, okay, if you pick this one, you draw this line or that boundary. What's going on there?
It's where it's like transitioning from solid to liquid.
Or liquid to solid.
Yeah.
They're in equilibrium. The solid and the liquid both have the same chemical potential. So they're coexisting on all these phase diagrams, right? That's where the states are coexisting. They're at equilibrium. Okay. Let's start, I think. So we've heard of solid, liquid, vapor. Well, let's just go with this order. Let's start with this. Right, there'll be some method to the madness here. Start with vapor pressure. If I have oh, here's some water. Shelby's got some water. Okay, so let's say, we'd have to do this. We'd have to pop it open. Okay, so we pop it open. You wait long enough, pretty much what's going to happen? All of it will evaporate, probably, right? Okay, so let's refill it up. Now this time let's seal everything. So we can still breathe in here. It's just sealed, right? We're a closed system. So it's sealed. We're like an Erlenmeyer flask with a rubber stopper on it. Okay. Would all that stuff evaporate or not? If it does, we dump some more in there. We have a faucet in our closed system, right? So we fill it up. We keep filling it up until the level doesn't change anymore. Okay? So that would mean
The vapor pressure. Yeah. Vapor pressure. Cody.
That would mean what?
Take this one.
What does that entail? Because now we're going to start using these terms on here. We have the total pressure of the room, but that's not just water vapor. We can say what? The total do you remember? Let's back up even more. Somebody's law starts with a D. Dalton's law. And pretty much this is all getting into vapor pressure. Dalton's law is PT equals PA plus PB plus PC plus, I just keep adding them up. And all these, so PT is what, you have a manometer or some pressure gauge in this room, you measure the pressure. We can't measure PA, PB, PC. These are all theoretical ideas. What are they called?
Partial pressure?
Partial pressures. Okay, so go back to our room. That's nice and sealed. We have water in Shelby's container, and finally we got to the point where it's not, it's evaporating, but it's condensing at the same rate. So the level's not changing. So we can finally say, what about this room?
The vapor pressure is a partial pressure of the room.
The vapor pressure of water is equal to its
it's equal to its
partial pressure in the room, right? So you pick one of these. Pick one of these. Water's one of them in this room. Right? Water's one of them. So finally, you get to the point where, finally, that the water's not the level isn't changing. It's always evaporating. The level isn't changing, so then the vapor pressure of water is equal to its partial pressure in this room. Now, what's so big deal about vapor pressure of water? Do you remember seeing a whole bunch of these little tables? Right? And they said, the vapor pressure of water, 25 degrees is so many millimeters of mercury. Vapor pressure at 50 degrees Celsius is so many millimeters of mercury. In Gen Chem, we had to mess with this. We messed with it in class, we messed with it in lab.
It determines the temperature that you need to boil. Or if there's more pressure, you need a higher temperature to boil.
Yeah, you're getting there. You're a little bit ahead of me. In Gen Chem, what we use the vapor pressure of water tables for is when we collected a gas over water. And then we had to subtract out from our total pressure the vapor pressure due to water to get the pressure of the gas. Then we could use PV equals nRT to get what we wanted. So that was Gen Chem. But here we're talking about vapor pressure, that concept. Now what Eric was talking about, we're going to build up to that. What if, go back to the room idea, it's sealed. Now I don't have this amount anymore. It's not changing level, it's still evaporating. What if I had half? Would that change our story? In the sense that the partial pressure of water is the vapor pressure of water. No, it doesn't change. What if I brought it all the way down to one drop? It doesn't matter, right? It's independent of the amount. I gotta have at least one drop. Okay, now let's go back to an even stranger idea. Where we're talking about vapor pressure is what part of this phase diagram?
Vapor part.
If you're going to circle the boundary and say vapor pressure of that compound, it would be 1, 2, or 3.
What would it be?
It would be 3.
Yeah.
It'd be boundary number 3. That's vapor pressure. Which you are actually creating one of these or finding one of these boundaries with the Ramsey-Young apparatus. Which boundary is that? Now, not everyone's done the Ramsey-Young. Who has done the Ramsey-Young lab?
The vapor pressure?
Yeah, the vapor pressure. So if you've done the Ramsey-Young lab, you're actually measuring, you're making little points as to the vapor pressure of whatever that compound. I think it was acetone or something. Yeah. But how did you do it? Change the pressure and heated it up until what happened? Yeah, it started condensing. There's a word up here. There's a word up here. You heat it up until it started boiling, right? So you had it at, you started out with a temperature, sorry, you started out with a pressure really high or really low? Really low, and it boiled at a low temperature or a high temperature? Low temperature. And then you increased some pressure, and then the temperature went up because it boiled at a higher temperature. That's what Eric was talking about, right? So the higher the, and that's how it is for every compound known to man. The higher the pressure, the higher the boiling point. So you can call this the boiling point curve, the vapor pressure curve, whatever one suits you. But where I think things get interesting to me is why did it boil? When does something boil? What's the...
The vapor pressure has to be greater than the atmospheric pressure?
Okay, the vapor pressure has to be greater than the atmospheric pressure or equal? Equal or above, right?
Yeah.
So the vapor pressure has to be equal to the external pressure, and then things boil. Exactly. So that's the only thing that determines boiling. And that's the entire bulk. It's not just the surface that boils. It's the entire bulk of that solution wants to turn into a vapor when the vapor pressure reaches the external pressure. And how do you raise the vapor pressure? You just raise the temperature. So you keep raising the temperature until the vapor pressure is the same as the external pressure, and then it boils. So why could you say in Colorado, Gloriana, way up there in the mountains, Randy and Jane have to cook their macaroni longer or shorter than you down here in San Antonio, Texas?
Longer.
They have to cook it longer. Why?
Because they're at a different pressure.
Keep going.
The altitude.
They're at a pressure that is
That is higher.
that
Than here.
that is
The altitude's higher. But
Yeah,
that
the
would be
pressure is lower.
they're at a lower pressure. Okay, keep going. Finish the whole story. They're at a lower pressure.
I think I'm done.
No, you're not. They're at a lower pressure. So their water that they're trying to boils at a
At a higher temperature.
Lower pressure.
Lower pressure.
Yeah, lower pressure, lower temp.
Lower temp.
lower temp.
Lower pressure.
So they can't get the water as
Hot.
hot. They can't get the water as hot. Okay. Now, if you really remember your Gen Chem, you can answer this. They want their water, the old Jane and Randy, whoever I said, they want their water to boil at Gloriana's temperature. What's a super cheap thing they could do?
That's all.
Add salt. All right? Add salt. Okay. That'd be worth a piece of Halloween
It's a
candy.
today, right?
Okay. So that's the thinking there. Is whether I had a droplet of water or a whole bulk of water, it doesn't matter. The vapor pressure has to reach the external pressure, and that's when things boil. Shelby, what's sublimation? Sublimation. So we have 1, 2, 3, 2.
It's like one.
Without sublimation, I used to, in Minnesota, I don't know, it took a while for this to get out of my system. Wanted to go back there for eons, right, until it finally dawned on me, boy, there's so much better here. But the point is, I delivered newspapers the whole time I was a kid in Minnesota. In the winter time, it never got never got above freezing. I mean, we're talking about 3-4 months in a row. It never warmed up, ever. Morning, day, night, it never warmed up. So I'm out there delivering newspapers. I see the snow bloody disappear. How? It never warmed up.
Sublime.
Sublimation. Going from what to what?
Solid to gas.
Solid to gas. So which number would that be?
1.
That'd be number 1. Solid to gas. Sublimation. Yeah. Well, vapor pressure's on there twice. And we talked about boiling. Here's a boiling in space movie. Let's see what the heck this is. See if it even works.
zero pressure. So,
See the difference? What they're trying to illustrate here is that when you remove gravity from the issue, it's trying to bring across the point that it's the entire bulk that's trying to turn into a vapor, and not just, you know, the stuff around the filament or
back to
something.
that point of having one drop or a whole thing, it's like it all boils at the same time or whatever, right?
That's what they're. It's still not a great image because you got the filament down there, and that's where the bubbles originate, kind of. But the point is that you see this huge vapor in there. So boiling is the entire bulk turning to a vapor. Normal. Okay, we have boiling points. Normal. What's the difference?
1 ATM.
Yeah, there you go. 1 ATM. So how do you read these things? Right? We'll get into reading some of these later, I guess. But if you wanted to read, let's clean this up. Oh, Alyssa, let's say this is for water, okay? And we'll talk about how to identify whether it's for water, how to draw water's phase diagram. And this one's messed up for that. But anyway, how would you figure out the boiling point of water? Right, the normal boiling point of water. Now we know it's 100 degrees Celsius, but how could you read that on something like this? How are you supposed to use this to figure out what boiling point is? They're not interested in 1 atmosphere. They're interested in 2.5 atmospheres. Right? How do you read these things? Does anybody know? An idea?
Find your pressure on the y-axis.
Yeah,
and match
good.
it with the
Find the pressure you're interested in. Let's just pretend it's right here.
phase boundary that you're looking for.
So then go all the way across. Stop here.
Nope.
Keep going. Good. Stop there. Then go
Down.
down. And there's your temperature. There's your boiling point. So if you're interested in boiling points, look here. If you're interested in freezing points or melting points, you'd look where? Yeah, solid liquid. And do the same game, right? Go down. Okay. Triple point. Okay, so we've got some. You go to, I don't know, the guys go to Mars. Right? They're working on that. I don't know if they're ever going to get there. The cosmic rays are a huge problem. Do you know that the guy's bones simply dissolve as you're in space? And they don't know how to fix that either. So there's some huge hurdles to overcome. And don't even argue about all the politics, but the point is there's some huge hurdles to overcome. Anyway, they get to Mars, and they want to do some little studies. And they forgot the damn thermometer. Let's make up a story. So what could they do? What's the temperature in Mars? Ah, shit. Joe, you forgot the thermometer.
They can see what temperature something boils at. I mean, see the pressure something boils at.
But they don't.
Yeah.
But Joe not only forgot the thermometer, he forgot his pressure gauge.
The triple point, raw theory.
There you go. Find the triple point of something. All right. Dig up. I don't know. I guess. Hopefully, if they're going to Mars, hopefully the little robots found some water. Right. So they get some water. Right. Get it. All 3 states are in equilibrium: solid, gas, liquid. Right? They're all there. You know, it's defined for that compound. Doesn't matter what gravity is. Doesn't matter what the environment is. Doesn't matter what the pressure is. If you know what the triple point is, you're good to go. You know exactly what that temperature is going to be. So it's an intensive property of every compound. So maybe water's not the one to use. Maybe something else. Okay. Critical temperature is kind of interesting, I think. So you heat something up, and then you have this nice liquid curve. Remember we played the game where, okay, what's the boiling point at this pressure? You just go across. Well, sooner or later, you keep raising the pressure, and then you hit the end of the liquid vapor curve, and then you try to raise the pressure some more, where do you go across? So what the heck is going on up here? And you're supposed to draw the lines like this. It's kind of misleading how they have it. What's going on in this area all in here? It's really nice to think, oh, we have what states for a compound?
Solid, liquid, gas.
Yeah, but life is much more complicated. I mean, look at some of these. Look at water. Look at all these ices. Life is going to get much more complicated. We have solid, liquid, gas. Great. But there's also starts with an S. Supercritical fluid. If you like what kind of coffee, this is how they make it. I think I told this story in Gen Chem, maybe, if you had me.
Decaf.
Decaffeinated coffee. This is a really clean way to decaffeinate coffee. And I don't know who figured this out, but if you take carbon dioxide and you get it into its what state? Supercritical fluid. If you create it into its supercritical fluid, and what pressure and temperature is that? Just find the phase diagram of carbon dioxide, and we'll look at it. And it's in its supercritical fluid state. Man, it dissolves caffeine extremely well. So you get all the caffeine to dissolve from the coffee beans, right? And the CO2, and then warm it up. Well, the CO2 goes back into CO2. You could reuse it. It's fantastic. Super cheap way and super clean. Won't mess with the taste either. It's not supposed to. Okay. So here's some pictures of it. Now, what is a supercritical fluid, though? We have an idea what a liquid is. We have an idea what a solid is. We have an idea what a gas is. I think for me, the easiest way to explain a supercritical fluid is, I don't have the word down here. It's too dense right in here, this area. It's too dense to be a gas. It's too dense to be a gas. But then it's not dense enough to be a liquid. I don't know, that's kind of the best. It's a difficult explanation. That's why I try to get some movies here. So what this movie is heating from below to above the critical temperature.
As the temperature rises, the liquid meniscus flattens. This flattening is due to the increased energy of the benzene molecules. The forces due to increased molecular movement are beginning to overcome the attractive molecular forces at the surface. At the edges of the vial near the liquid surface, the benzene can be seen boiling. When the critical point is reached, the meniscus disappears and only diffraction irregularities are present due to temperature gradients. Here, the forces due to molecular movement overcome the surface tension, and the separation between liquid and vapor disappears. Above the critical temperature, only the gaseous phase exists. A gas above the critical temperature cannot be condensed into a liquid, since the molecular attractive forces are dominated by the rapid molecular motion.
So it's gone. No more meniscus. Kind of interesting. Here's from cooling from above to below the critical temperature.
As the temperature decreases, the meniscus reappears at the critical temperature. The molecules in the gas move more slowly, allowing the attractive forces between the molecules to become dominant. At this point, separate liquid and vapor phases form. Note that the thermometer is present only to indicate increasing and decreasing temperature and an approximate range for the critical temperature.
So it's almost like a constant transition state between liquid and gas.
Yeah,
It's
it's
like a gas that's not a gas almost.
yeah. I don't know. It's really it's not an easy concept. That's why I just showed you pictures of it. It's a gas. It's not a gas. Exactly. It's kind of odd. Okay. Oh, let's answer some questions here. For if in this plot, how does the boiling point change with pressure in this plot?
Varies directly.
Does it go in other words, how does it vary? As I increase the pressure, the boiling point goes, everybody agree? Boiling point goes up. How about if I increase the pressure, what happens to the melting point? Kelly, let's pick on Kelly. Haven't picked on Kelly for anything. It decreases? So crank up the pressure. Right, I just pick one at a time. So we go across. Here's the. Am I looking at the right curve? Am I looking? Yeah. Okay. So here's the melting point. Bring up the pressure. Go down. The temperature looks like it's increasing. So with this plot, the melting point increases with increasing pressure. Okay. Does it have to always? No. Yeah. And this is most every compound known to man has that type of plot, and that type of boundary between solid and liquid, and that the melting point increases as you increase the pressure. Kind of makes sense to me, but water is the exact opposite. Out of all, and that's just another curiosity, I think, for water and life on this planet, is add this to the list of all these oddball things. Water behaves completely opposite of essentially every compound known to man. The line's going back. The line's going back. So by the line going back, now as you increase the pressure, the freezing point drops. And we'll see the real huge significance of that later when we start talking about this. But just realize water is a real oddball.
Less density of freezes, right?
Density's the key. Yeah. Not everything does that. Okay, I think we've talked about all this stuff pretty much. All right. Okay, we talked about normal boiling points in 1 atmosphere, triple point, we talked about that. Some typical phase diagrams. This one's carbon dioxide, right? How about Alyssa? Didn't you help out with the last thing that they did for the Chem Club? And you guys bought some dry ice. Yeah. So dry ice is really what? What is dry ice? Does anybody know? Yeah, I think it's CO2. Good. Frozen CO2. So we're talking about dry ice, right? Where would that means CO2's phase, where would that discussion or that occurrence with dry ice fit on this phase diagram? Where should you be looking?
That's sublimation.
That's sublimation. Yeah. Okay, so and our temperature is, what's our temperature in Kelvin?
What do you mean our temperature?
Yeah, because this is Kelvin.
Mm-hmm.
What's room temp in Kelvin? Gloriana, what's room temp in Kelvin?
Like 78 plus 273.
Okay, 78 Fahrenheit plus 273.
Oh, I mean.
So now what's the room temp in Celsius? She's got the right thinking here. Yeah, somewhere around 25, right? And then 273. Yeah, around 300 Kelvin.
Yeah.
So we're way the heck out here. But what's our pressure?
1 atm.
1 atm. So if I was going to make a point, I would say, somewhere around here. That's where dry ice wants to be. According to this phase diagram, it's a plot of the most stable or the most states, right, the lowest Gibbs energy for each state, at different pressures and temperatures. Well, if you're at 1 atmosphere and 300 Kelvin, let me just kind of put your finger right here. That means CO2 wants to be a gas. All right? But you went out and you bought dry ice. Dry ice is CO2 not as a gas, but as a solid. Well, it's got to convert to a gas. You can't stop it. That's nature. Because as a solid, that's not its lowest chemical potential. So it's going to go to a gas, and you can't stop it. And that's what this phase diagram is all about, helping you predict.
It's like if you're at a pressure below the triple point,
So
you can't do anything to sublime solids. Because you can't have a liquid, right?
yeah, that's a good point. If you're, well, it has to be 5 atmospheres. Yep.
Yeah, if the triple point's higher than the...
Yeah, so if you're above 5 atmospheres, you're going to have to, you can still have it turn into a solid to a gas, but you're going to have to go through the what phase? The liquid phase. If you're above 5.11 atmospheres, it's a good point. If you're above 5.11 atmospheres, but you're at room temp, like maybe up here, you're going to, you go and buy some dry ice, but really crank up the pressure on it, yeah, it'll turn into a gas. It'll, sublime, but it's going to go through that liquid phase. So that's really not sublimation. That's first melting and then going from liquid and boiling, right? So first you got to melt it and then you got to boil it. And it makes sense. It's heating up, right? Because it's too dang cold. It's supposed to be way out at 300. So that's pretty much how all these work. What if, let's try another one. What state am I, Jeffrey, what state am I if I'm at, let's say 200 Kelvin and 1 atmosphere? What state should CO2 be in? Or will it be in if you give it long enough?
Gas.
Gas. Everybody agree? Gloriana, how about 300 Kelvin and 70 atmospheres?
Liquid. Or
Shoot. I thought I saw it easy. Now I don't see it so easy.
Yeah.
What?
It's a tough one.
Yeah, that is a tough one. But we're looking. I don't think everyone can. If you see it as a tough one, then you're reading this right? Because where's 70? I don't know. It's probably gas, right? But yeah, that's the idea. That's the idea. So water. So water has a critical point. It has here's vapor, right? Our normal freezing point. Normal freezing point means the pressure must be what? 1 atm. So that's why they went across here, and they went all the way over to the solid liquid line, right? So there's our normal freezing point or melting point. Okay. So they're showing you a lot more. Usually we see a phase diagram like this, right? Just get rid of the rest of it. And this is the part we're looking at. And if you look at just that part, if you look at just this part, man, it looks really similar to what we did up here, except what's different?
Melting line.
Solid to liquid line. It's the opposite direction, right? So as you crank up the pressure, the melting point goes down. Okay. Why can you ice skate?
The pressure from the skates melts the water.
Yeah. Because the pressure is going to be really what under that skate? High, right? It's really narrow. Right? The pressure is going to be really high, so the freezing point drops, and they say it turns into a layer of liquid. Except now they don't believe that anymore. They're finding that there's just not enough pressure to do that. So over the typical dude skating, they're saying there's just not enough pressure to turn that into liquid. So they've been looking at ice a lot more closely, and they think that ice actually has and by nature, it has a thin layer of liquid on it in the first place. And that's what's allowing you to skate. That's just what they're saying nowadays, that I used to think as exactly as Jeff said, that that's how you can ice skate. That it's that blade. You crank up the pressure, it just melts under there. Then you skate off, and then it refreezes again, right? But at a microscopic level, there's an extremely thin layer of liquid water. That's what the science is saying. Maybe they're using spectroscopy or something. I'm not sure what they're doing. Man, you think that could be something that we could do here, because you're just looking at the surface. Okay. I want to make sure I have more volume. I don't want to, I think that would be here. Okay, I think we better finish the story. So, we said the curve's going back. And a consequence of that is because of the density, what Eric said. What's more dense, solid ice or liquid water? What's more dense?
Water.
Liquid water, because ice floats. Okay, so this is, without this happening, without this line going back, complete opposite of every other compound known to man, without that line going back between the solid and liquid phase, ice wouldn't float. Ice would sink. Pretty much every compound, when you freeze it, it gets more dense and it sinks. What would be the consequence of, this is a kind of an overall question in my mind, what's the consequence of ice floating regarding, if you believe in evolution, what's the consequence?
Less.
Yeah. Well, all the way back. Yeah, you use some land bridges, but the point is you gotta have life in the first place. They say life came from water, right? Isn't that the? You guys are the biologists, right? So, life is supposed to crawl out of the lakes or whatever, right? Originated there. So, well, I assume it was cold at some point way back then. You had these ages. Where would lakes, streams, rivers, oceans freeze?
The bottom.
They would, yeah, it's really coldest where in a body of water? At the top or the bottom? I'd say at the bottom, right? Because the sun's not reaching it. Okay, so you get a little ice particle down there, and is that little ice particle going to go up or is it going to go down if it was a normal acting compound where the solid is more dense? It would sink. So that little ice particle sinks. All the little ice particles start sinking. Well, then pretty much you're going to freeze from the bottom up. Everything's going to freeze solid. Everything. But that's not how nature works. Right? You form a little ice particle at the bottom of the lake or the ocean or wherever, it's going to go where? It goes to the top. So you get this, yeah, it's pretty darn thick. You go to Minnesota and, man, we were driving our trucks out there and everything out on the lakes because that ice is like 8-10 feet thick. Yeah, I mean, even deliver pizza out there. They put up road signs. But and build a campfire, it is the coolest thing.
Really?
But the point is without ice floating, I don't see how this whole idea of life could exist. So it's another oddball thing. Okay, and there's a lot of those kinds of things in nature that without it happening, I don't see how life could exist. Here's helium. I think that's helium. Shelby, can helium solid ever be in equilibrium with helium gas? The answer is no, and she's right, but can you see why? Solid's way up here, gas phase is way down here, and then they call this a lambda line. So nowhere is there a phase boundary, like between solid and gas. So you can't have sublimation. You always have to go through that liquid phase for helium. They call it a lambda line type of activity there. What happened to superfluid?
Yeah, it's bottom left.
Where is it?
liquid He2 superfluid? Right next to your clicker? Your mouse.
Oh, here it is. Yeah, superfluid. Okay. I thought I had a movie on that. Yeah, here it is. Okay. I don't think you have this. I found this morning. So here's a little movie on superfluid. That's kind of cool. Again, how do you imagine something? First, what is it? If you have helium at, what the heck? Extremely cold, very low pressure, well, not that low, just above 1/10 of an atmosphere, right, or 1/10 of a bar, you can get a superfluid. Well, what's so special about a superfluid? It doesn't have any, the V word, viscosity.
That's right.
It doesn't have any viscosity. Let's see if this works.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particularly is happening. Well, this is really one of the great phenomena in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them.
Really, that fountain will keep going forever? How the heck does it do that, right? 'Cause it takes energy.
Yeah, that's what I was thinking.
Okay. So, and then I've always been curious about this, so I looked it up. What is typical ice? I mean, look at all these different ices. What are they? This is water, by the way. This is water. How do you go from, you see all these different ices? Ice 1, ice 2, ice 5, ice 6. Here's ice.
So I refer to like the different crystal structures of ice?
Exactly. Different crystal structures of ice. So the hexagonal ice, this is what we typically see, right? That's the only type of ice we've ever played with. I mean, it all probably looks the same, and you have to do X-ray crystallography on it. And I thought it was kind of interesting, the different types of ices. That's why I just kind of Googled this stuff. You can make amorphous ice. It's like glass. There's no, it's just a random order. And you have to cool it down 1,000,000 degrees per second for this to happen. But you can make amorphous ice. There's cubic ice. It's like diamond. All the oxygen atoms are in the same location as diamond. There's ice 1. So again, where are these? Well, like ice 1 is making the pressure around between 1 and 2 atmospheres, but the temperature is around 273 or so Kelvin, 0 degrees Celsius. Pretty much, I mean, we might have messed with these types of compounds, not even known it. So you have your 6-membered rings, and they're just layers. And in ice 2, you have pretty much ice 1 again, but one hexagonal film over another, and they're interacting with each other. And And then these pictures just get more and more complicated as they go on here. But at least this ice 7, at least you can kind of tell what's a little more visual, I guess. Otherwise, it's really hard to see what any of these really are doing.
It's kind of weird, like on the curve or whatever, the temperature, like how the curve of that solid to liquid line is, the ice and the liquid line, how it, is going backwards and then going forwards.
It does.
Yeah.
It does. Starts acting normal after a while.
Yeah, so like.
You got to be way up to really high pressures to do it.
Yeah, I guess once you get a high pressure, then that's weird.
Yeah, it's strange. So, this is supposed to be 2 of these intercalated with one another. Talked about superfluid, and then we're about out of time. That's good, right? And then we can finish this. So you can work on some of the homework, and then we can finish our talk on next class period.